So I just want to take a couple minutes to talk about what a capacitor is. Now, hopefully you remember from previous weeks that it's really just a two parallel plate system where each plate here has equal and opposite charge. So we've seen, okay, there's positive charge and there's negative charge. The idea here is really to understand how the charge got there in the first place. And the idea is that we can hook it up to a battery, where a battery has a positive terminal and it has a negative terminal. Between the two terminals, we're going to have a potential difference, right? I should say between the two terminals, we have a potential difference that we're going to call delta V battery. Now, the idea is that this positive terminal is going to cause the positive charges in the wire in the system to be repelled, right? So like repels like, and it's going to repel this way and land up on this plate here. Now, that's going to cause the positive charges on this side of the system to also be repelled and end up going this way. So we essentially have this loop here. But the important thing is that nothing is passing through this empty space, right? Because we're just dealing with electric fields here, and you can feel things at a distance. So here we have the positive, and the positive keeps going this way. Now, what's going to happen is this positive charge is going to keep building up on this plate. But every single time a positive charge ends up on this plate, it gets harder and harder for the battery to push that positive charge here. And the idea is that, of course, like this is positive, we're trying to force another positive on it. That positive is going to be repelled. And at some point, it's going to max out. And that point is when the potential difference between our parallel plates is equal to the potential difference between the batteries. And that's what I try to explain right here. Right, so it's not an infinite process. The battery can only push so much charge onto the plate. And like I said, the max is when delta VC so the potential difference between the capacitor plates is equal to delta V battery. This is also known as an electrostatic equilibrium. So the rest of this is really just going to be trying to quantify this situation. We know that the electric field between two plates is equal to sigma over epsilon naught, where sigma is just charge divided by area. Here I just say eta because sometimes people use the letter eta instead of sigma. All means the same thing. Now what we've also seen last week is that delta V, so the potential difference between two plates, is equal to E times D, where D is the distance between the two plates, and this is only for a uniform electric field. Now all I'm going to do is take delta VC here, and I'm going to essentially shove this here. So what is E, right? Shove that into this equation here. And then isolate for Q. So that's all that happened here, where I wrote out Q in terms of delta V. And this is what we get here. Now, what we're going to do is define a new variable, and we're going to call that variable the capacitance, where capacitance is equal to Q divided by delta VC. And then here, of course, if we look at this equation as well, okay, then C is equal to epsilon naught A divided by D. And remember that this here is only valid for this parallel plate capacitor system because we're dealing with a uniform electric field. Like this equation does not hold true for non-uniform electric fields. So what really is the capacitance? Well, we kind of want to know like how much charge can get shoved onto this plate. And well, we know that it's related to delta V battery, right? It's like, well, it depends, like what's the potential difference? But it's also related to how big is my plate, right? How far apart are my two plates? And that's kind of what the capacitance is expressing. It's saying the amount of charge you can shove onto this plate depends on the size of the plate, in part. And that's what we see here, where C is equal to epsilon naught, and then A is the area of my plate, and then D is the distance between my two plates. Now the units of capacitance is the farad, and 1 farad is C divided by D, so Coulomb divided by volt. And what you see in the textbook is that a farad is very, very large. So we don't usually talk about farads, we might talk about like microfarads. The really cool thing about capacitors is that they maintain their charge and potential difference when disconnected. So you have the system here, right? It's connected to the battery, we're shoving this charge on it, we create this potential difference, And then you can remove that battery. And what you're going to see is the positive charge stays here, the negative charge stays here. And what we're going to see later is that this capacitor can in essence act like its own battery when we connect something like a resistor to this side here. But we're not going to talk about that yet. So there's two types of circuits that we are going to encounter in this chapter. The first one is called a parallel circuit, and the second one is a circuit that's in series. Now the symbol for a capacitor is this here. So we have the two wires, and then we have our two plates like this. Now when the capacitors are in series, so we have C1 and C2, when they're in series, you can take one side of them and connect it to the other. So take this side, connect it to the other. So this is parallel. That's very different than series, where here I'm trying to connect it to the other side and I have to run through this battery, right? So it's not the same. So here I have to go through a battery to connect it to this side, versus in parallel, they can just freely, via wires, get connected like this. All right, so now when we have a parallel circuit like this, we know that C1, capacitor 1, and C2, capacitor 2, have the same potential difference. The idea here is that this positive charge is forced onto this plate here, but there's also positive charge that's being forced onto this plate here. Right? So even if C1 maxes out and it's like, I can't take any more charge, well, C2 can, and it can keep taking charge until they both have potentials, right, where VC1 equals VC2 is equal to delta V battery. So they can keep taking charge until their potential differences are the same as that of a battery. And that's what we express here. On the other hand, they don't have the same amount of charge that's being pushed on them, because this is our equation for charge. So Q1, the amount of charge on capacitor 1, is equal to C1, capacitance number 1 times delta VC, Q2, C2, delta VC. And we're not saying that they necessarily have the same capacitance. Like this might be really big, this one might be really small, who knows. What we then want to do is figure out a way to combine them into something we call an equivalent capacitance. So it's essentially being like, okay, they have separate capacitances. What if we can combine them such that they act as though there's only one capacitor there? And that kind of simplifies our problems. So we're going to define this term C equivalent. The equivalent capacitance is equal to Q, the charge on that new capacitor, divided by delta VC, the potential difference of that capacitor. Now we know from here, well, they have the same potential difference, but they have different charges. So we're going to have Q1 plus Q2, that's how much total charge we have, divided by delta VC. So here we have Q1 divided by delta VC plus Q2 divided by delta VC. We know that this here is the definition for the capacitance of number 1, right, from here up there. And this is the definition for the capacitance of number 2. So that means to combine the capacitance, so C equivalent is equal to, well, what was the capacitance on number 1 plus number 2 plus ... Okay, so this is the really important equation, but what's also important is to understand that they have the same delta VC as well. Now the situation is a little bit different when we have our capacitors connected in series. So here, like I was saying, to connect the two ends of these capacitors, you have to go through the battery, and that means that they're in series. So when they're in series, they don't have the same potential difference. The reason for that is because this guy so the battery is forcing these charges, and at some point, this potential difference between C1 is going to equal the potential difference between the battery. I should write this one C1 and this one C2. And at that point, the charge is no longer going to be flowing because it's maxed out. It can't force it through the rest of the system. On the other hand, capacitor 1 and capacitor 2 are going to have the same charge. That's because we're going to have a certain amount of charge, positive Q, that ends up here, and equal and opposite amount ends up here, because that's a definition for a capacitor. And that's going to induce an equal and opposite amount here, which then induces an equal and opposite amount here. So they all have the same amount of charge, Q, on their plates. So here we have our expressions where delta V1 is equal to Q, because it's the same for both of them, divided by C1. Delta V2 is equal to Q divided by C2. Same idea, we want to figure out, well, what's the equivalent capacitance? We write that out here, so C equivalent, Q divided by delta VC. We know that delta VC is equal to delta V1 plus delta V2, and everything has the same amount of charge, so the equivalent capacitor is going to have the same amount of charge anyways. And then the thing is, though, we want to take these equations up here and plug them into this equation. So to do that, we have to inverse C equivalent. We inverse it like this, and then we get delta V1 divided by Q plus delta V2 divided by Q, which are our equations up here. And because of that, we get 1 divided by C equivalent is equal to 1 divided by C1 plus 1 divided by C2. So we see that these equations are quite different. So whenever you're solving these type of problems, the first thing you do need to figure out is, are they in parallel or are they in series? I'm going to be going over some practice problems for these, and then I'll also be covering energy stored in a capacitor in the next video.